Okay, good. So yesterday we started off with looking at some acids and some bases, and so we're going to go back and take a look at that unit and see how that then ties in with some of the things that we did do last year, and then some of the things we didn't do last year in Chemistry 1. I want to go ahead and start off with an idea that we studied in Chem 1 last year, and that is strong acids. Okay, strong acids are acids that totally dissociate. Okay, so they totally dissociate. Now, what does it mean to be strong? It means that it's going to all 100%, every single bit of it will break apart. What does it mean to be an acid? Well, our easiest definition of an acid is that the molecule starts with the letter H. The formula starts with an H. It releases a H positive, which of course we call a proton, because an H positive is a proton, because a hydrogen is a proton and an electron. And if you lose your electron and become positive, you're just a proton. And so what we're going to look at are some of the acids that we studied in Chem 1. For instance, we studied HCl. HCl is a gas that gets dissolved in water to make a compound called hydrochloric acid. Hydrochloric acid, when we put it into water, will totally dissociate and break apart into hydrogen ions and chlorine ions. It's a very, very reactive chemical. So, using the same sort of charts, the same sort of things that I've been doing with equilibrium, at the start, let's say we've got 0.01 molar HCl, like you had in your discovery yesterday. You would have no H positive and no Cl negative when we first prepare this. But really quickly, okay, really quickly, when you put the HCl into the water, it all breaks apart. 100% dissociates. So what do we end up with? Well, we end up with 0.01 molar H positive and 0.01 molar Cl negative, because one of these breaks apart and makes one of these and one of these. Okay? So this is total dissociation. This is, again, what we studied last year in chemistry. So I asked you yesterday to go ahead and calculate the pH. And we developed last year in chemistry the formula pH is equal to the negative log of the hydrogen ion concentration. All right? If you need a little cheat sheet for your calculator, let me know. I printed off some extra ones. You should have that with you, but you could also put it on your periodic table. I think it is on your periodic table. So let's plug this in and see what we got. pH is equal to negative log of 0.01. Okay? And so most graphing calculators work the same way, and that is, all we have to do is type in negative, not minus of course, but negative log 0.01 and hit enter. And it tells us what the pH is. And you might remember that this is 2 without having to punch it in. Why would we remember that it's 2? Well, if the concentration is 0.01, remember that 0.01 is the same thing as 1 times 10 to the negative second power, isn't it? That might be helpful because then the exponent is the pH. Okay? That's pretty easy to use when the number inside the digits inside the concentration are ones. Excuse me. But in this year's work, we want to move away from the strong acids that we worked with in Chem 1. Last year we focused a lot on nitric acid, sulfuric acid, and hydrochloric acid. These are all strong acids, okay? They all totally dissociate. They break apart into their ions. But this year, what we want to do is look at the acids that are not strong acids. They're weak acids, okay? So, if a strong acid is an acid that totally dissociates, a weak acid is an acid that does not totally dissociate. Okay? Now notice that in these two definitions, I didn't say anything about the pH. The pH can be very, 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 very low for strong acids, or it can be very high for strong acids. Okay? The pH can be really low for weak acids, or it can be high. Now normally it's a little bit higher, okay? If you remember, just to refresh, and again I think this is something that most of you picked up on yesterday, and we'll review it just a little bit later on in class today. But remember that the pH scale goes from 0 to 14. 0 to 7 are our acids, 7 to 14 are our bases. The 0 is where we are the most acidic. The 14 is where we are most basic. Okay? So that chart, and again, I think most of you from listening to your conversations yesterday and what you wrote in your discovery, remember that. Okay? That the higher the pH gets, the less acidic it is, until it gets to 7, and then the higher the pH gets, the more basic it gets, and that is, again, less acidic. I want to start off with a generic formula. HA is my generic monoprotic weak acid. Monoprotic, one proton, and generic because I'm just saying any hydrogen with an anion, okay, and that anion could be a variety of things. It could be it can't be a chlorine, a nitrate, or a sulfate, but it could be just about anything else, okay? Those guys are going to break apart and give us a proton and an anion with a negative charge for the monoprotic weak acids. Notice that I drew the arrows both directions to indicate that we're going to establish an equilibrium that is not 100% broken apart. Okay? It's not going to be 100%. It's going to be only some of this breaks apart. So, let's figure out our K. And we have a little addition to our constant today, and that is that this is called the Ka. This is the equilibrium constant for the dissociation of an acid. Okay? This is a dissociation equation. Okay? And now we're going to go ahead and write the equilibrium expression of that dissociation. And it's the Ka. Well, the good news is it's exactly what we've been doing. And exactly what we've been doing is we take the products and we divide it by the reactants. Okay? So that's not too bad. And we could use this general formula for all kinds of different acids that are weak. On the fume hood, of course to the right is the chemistry 2 cart. And along the wall, you can't see it, but along the side of the fume hood is a poster that has listed a whole bunch of different acids and their equilibrium constants. It's also listed, I believe, on page like 1124 in the back of your book. A lot of different constants for these different acids. I want to use one of them in today's discussion. And the acid that I'm going to choose is one of the acids that I asked you to work with yesterday in the discovery, and that's called acetic acid, which of course is the main component of vinegar. Now acetic acid comes from a gas called hydrogen acetate. Looking on your periodic table, on your polyatomic ion list, the very first polyatomic ion is called acetate, and it's C2H3O2. It's an anion that wants to gain 1 electron, an anion that has a -1 charge. So this is hydrogen acetate. Acetic acid breaks apart into hydrogens and acetates. Okay? So, let's write out the equilibrium expression for that. Well, it's just like we had over here. K is equal to the H positive times the anion divided by the acid concentration itself. Okay? And if we look this up in the back of the book, and again, the back of the book would give us values for the equilibrium constants at probably room temperature. I can't remember exactly what it is. I'd have to look it up, but I'm pretty sure it's at room temperature. This particular reaction has a K equal to 1.8 times 10 to the negative fifth. Okay? So that's for the dissociation of acetic acid. It's 1.8 times 10 to the negative fifth, and I looked that up. Is it page 1124? 1126. Okay, so it's 1126. All right? So let's go ahead and determine our question, and that is, in station number 2 in the laboratory activities yesterday, you had a 0.1 molar solution of acetic acid. What was the pH? Okay, let's determine what it theoretically should be and see how close our measurements work. So let's determine the pH of 0.01 molar acetic acid. All right? Well, here's what we're going to do. We're going to take our equilibrium expression and we're going to plug in the values that we know and the values that we don't know. Okay? Well, we know the K is 1.8 times 10 to the negative fifth. We don't know the hydrogen concentration. Okay? Because when we did the strong acid over here, we knew the hydrogen concentration because it all broke apart. But we don't know the hydrogen concentration because only some of this breaks apart, not all of it. Okay? So we got to figure out what the hydrogen concentration is. So I'm going to go ahead and let X equal the hydrogen concentration, because if I need to know the pH, I've got to know the hydrogen concentration, right? Because the pH is equal to the negative log of the hydrogen concentration. So that's really what I'm interested in. So for the H positive, I'm going to put X. Okay? Now, let's look at our stoichiometry. In our stoichiometry, it says that one molecule of hydrogen acetate breaks apart to make one proton and one acetate. So if I have X number of acid molecules breaking apart, I'm going to make X number of hydrogens, positive, and X number of acetates. Does that make sense? If I've got a molecule that breaks apart, no matter how many of them break apart, I'm going to make the same number of these two things. Okay? So therefore, my acetate concentration is also X. Does that make sense? Not too bad? So what is my HC2H3O2 concentration? Well, it started off as 0.01, but we know that X amount broke apart. If we stop and solve from here, we're going to have to use the quadratic equation. But we don't have to. And the reason why we don't have to is because our K is to the negative fifth power, whereas our concentration is to the negative second power. That's a 10 to the third, or 1,000 times difference. So in other words, we can go ahead and make that assumption that X is going to be small. And in fact, we're going to say that X is approximately 0. It is so small. Very, 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 very few of these break apart. So now we end up with, and I'm going to shift boards back over to here, okay? I'm going to shift back over to here, and let's write down what we end up with. 1.8 times 10 to the negative fifth is equal to X squared over 0.01. Okay? You see what I did? X times X, X squared. 0.01 minus 0 is 0.01. Okay? Well, now this becomes pretty simple. Let's cross multiply. 1.8 times 10 to the negative fifth times 0.01 is 1.8 times 10 to the negative seventh. And that's equal to X squared. Let's take the square root of that. Okay? Let's take the square root. So the square root of 1.8 times 10 to the negative seventh is an X value, which of course is our hydrogen ion concentration, of 4.24 times 10 to the negative fourth molar. We said X was the hydrogen ion concentration, and that's what we solved for. Okay? So let's answer the question. What's the pH? And the pH would be the negative log of the hydrogen ion concentration. Okay? So I'm just going to keep it in my calculator, get negative log of my answer, and they get about 3.37. You know what, with our equipment, we would probably just round that to about 3.4. Okay? What was your pH in your activity number 2 yesterday? 3.3. Yeah, 3.3? Yeah, okay. So we were in the ballpark with our pH meters yesterday. With our acid. Okay? So hopefully that makes some sense. And what we're trying to look at here today is the idea that when we had the HCl, the pH was 2 for a 0.01 molar concentration. With this acetic acid, the pH is 3.4 for a 0.01 molar concentration. Same concentration, different pH, because not all of these guys break apart. Only some of them break apart. Okay? Well, what about bases, though? All right? So we talked about the idea that bases have a pH range from 7 to 14. And of course, bases are typically, if we look back to what we studied last year, strong bases. Okay? Strong, again, means that these guys are going to totally dissociate. Okay? And most of these guys are hydroxide compounds. Okay? Not all of them, but many of them are. We worked a lot with sodium hydroxide and potassium hydroxide, and we used magnesium hydroxide and calcium hydroxide. All right? And so they totally break apart, just like with our acids. We can figure out their pHs from their concentrations. Okay? But what about a weak base? Well, as I said, weak doesn't mean that the pH is necessarily lower. Weak bases could have high pHs, okay? But weak bases are going to not totally dissociate, okay? And so therefore, we want to try to look at some of those compounds. One of my favorite compounds to look at is the compound ammonia. It's a very, very, very important weak base. Last year, I explained why ammonia was a base, because it did what Bronsted and Lowry tell us a base is. It gains a proton, because Arrhenius just said, well, they got to be hydroxides. Not true. They could gain a proton, and that's what this guy does. He's also a pretty good example of a Lewis base. All right, if we draw him out, he's got a pair of electrons he wants to donate. But let's talk about what Bronsted and Lowry meant when he said he would gain a proton when we put him down into water. Because ammonia is actually a gas. And when we put that ammonia gas into water, what we see happen is that the water actually acts like an acid and loses a proton. Okay? It loses an H positive, and the NH3 gains that proton, gains that H plus. So let's take NH3 and give it an H and a positive charge. What would it be? Well, it would be NH4 with a positive charge. And if you look at the back of your periodic table, at the bottom of your polyatomic ion list, you probably would find something that you're familiar with, and that's our good friend ammonium. Ammonium is an ammonia molecule who's gained a proton. Okay? So this is acting as our base. That's acting as our base. What's left over from our water molecule, if an H positive leaves, that would be an OH negative. So this, again, ties back in with what Arrhenius said, that when bases dissolve in water, they release hydroxides. And this guy did release a hydroxide by gaining. And the good news is, it's just like what we've been doing for 2 weeks, and that is, it's products over reactants. And so if it's products over reactants, we have our NH4 positive times our OH negative divided by our NH3 and divided by our HOH, or our water. Okay? Now remember what all of these parentheses, square box parentheses, stand for. Right? These are the molarities. The molarity of NH4, the molarity of OH, the molarity of NH3. And what's funny is, how do you have a molarity of water? Moles of water divided by liters of water? It kind of sounds silly, doesn't it? And so what the consensus is that any time we see this, and again, this would have to be for water, because we could dissolve, we could have other situations with some other types of reactions. But when we see this in our dissociation, we're going to put in the value 1 for that number. Of course, when we multiply and divide by 1, that basically eliminates it. It's just like it's not there. Okay? Well, it has to be there in the equation to understand what's going on, but in the calculation, it's not going to exist. Okay? Now, funny thing, I picked this one out. I picked out the acetic acid because it's pretty common. I picked out the ammonia because it's pretty common. And one of the interesting things about them in the book, and Calhoun can back me up on this, if you look at the next page, look at the top of the next page, and you see ammonia, and its K is? Yes, kind of a weird, serendipitous, sort of coincidental sort of deal, that it has the exact same value of K as the other example problem that I did today. Okay? And that's very, very coincidental. It's not anything, it's not like, oh, hey, they're all going to be that same number, right? No, I'm afraid they're not. It's just the two that I picked to show you in lecture actually have the same K at the temperatures that they're listed in the book. Okay? So, here's our question. What's the pH of a 0.1 molar NH3 solution? When we dissolve 0.01 molar NH3, what will end up being the pH of that particular thing? Okay? Well, let's plug and chug, shall we? K sub B is equal to the NH4 concentration. I don't know that. Okay? Don't know what the NH4 concentration is, so I'm going to go ahead and let X equal the NH4 positive concentration. Okay? I'm going to write that up there. I like to write that up there because then when I solve for X, then I can go back and say, oh, I wonder what X was. Why did I solve for X? What is X? X is the ammonium concentration. Okay? So I'm going to put that up there. Okay? I'm going to also then signify here that the X must also be the hydroxide concentration, shouldn't it? Because if I take this reaction and I have X number of these that actually react, because remember, not very many of them are going to react, I'm going to make X number of these and X number of these. Okay? So that's my hydroxide concentration. What is my ammonia concentration? Well, it started off as 0.01 molar, but X amount broke apart. And what's my water concentration? We're just going to put the number 1 in there. Well, just like our last problem, this one simplifies very easily too, that we're going to go ahead and make the assumption that X is very, very small, practically 0, and so therefore we're going to rewrite this equation to say 1.8 times 10 to the 5th is equal to X squared over 0.01, and we're going to cross multiply and get the same thing. Okay? And when I say we're going to get the same thing, but we're going to get the same value of X as we did in our previous problem. But the value of X in this case is the value of the hydroxide. The value of the hydroxide ion. Okay? And the value of the hydroxide, and it's also the ammonium, but I just don't care about that. Why do I care that the hydroxide concentration is 4.2 times 10 to the negative 4th? Because I can calculate something that we call the POH. Remember this guy from last year? Okay? What is the pOH? The negative log of the hydroxide concentration. The negative log of the hydroxide concentration. So I'm going to calculate the pOH, and that value will turn out to be 3.4. Okay? 3.4. Is that the answer to the question? No, it's not. Because you see, the question says, what's the pH? We don't actually measure the pOH. We measure the pH. And so what do we know about pH and pOH? Well, pH and pOH always add up to equal to number 14. And we're going to go through a little calculation here in just a second to prove that to you, to show you that. But for right now, we're going to say that the pH plus 3.4 is equal to 14. Therefore, our pH must be equal to 10.6. And does that make logical sense? Should the pH of a base be 10.6? I say yes. The pH of the NaOH that you did in step number 5 yesterday should have been about 12. That's a strong base, okay? The pH of what we did in number 6 should have been less than that, 10 point something, okay? Now, a couple of things then that I want to follow up on to make this understandable. And that is, let's do follow up and talk about this idea of water and how it associates. And to do that, what I want to do, and this may be a little bit out of order on what I gave you, Taylor, but it's in there, okay, is I want to talk about water molecules, and I want to talk about the back of your discovery. If you flip it over and look at the back. And the back of the discovery shows a cartoon, kind of a silly cartoon, but a cartoon about the idea that if we take a random sample of water molecules, okay, most of the water molecules are going to be H2O. They're going to be HOH. They're going to be together. They're bonded, okay? They like each other. They stay together. But we find that 1 out of every 10 million water molecules will naturally be broken apart. 1 out of every 10 million water molecules does this right here, okay? Now that doesn't seem like very much, does it? Especially when you consider things like there's 10 million married people in America, 10 million married couples in America, and only 1 got a divorce. I mean, that really puts it in perspective about how very few water molecules actually break apart. Just a natural selection of it, okay? But what this does is this helps us understand our pH scale better. You see, if I write out the Kw for this, Kw, which is the equilibrium expression for water, it would be H positive times OH negative divided by the water concentration. Well, we already know what the water concentration is. The water concentration we've defined to be the number 1. What's the H positive concentration of water and what's the OH negative concentration of water? Well, flip back to the front of your discovery then and look down at the bottom 3 questions down there. And I ask you, what's the pH of water? And everybody knows that the pH of water is 7. Well, if the water has a pH of 7, what's the hydrogen ion concentration? So let's take our calculators and let's do this, okay? And following your instructions on your calculator, what we need to do is hit second log negative 7 and hit enter. In other words, you're saying 10 to the negative 7th power, which is, bless you, 1 times 10 to the negative 7th power. So our hydrogen concentration for water is 1 times 10 to the negative 7th. Okay? Now let's do some stoichiometry, baby. If 1 water breaks apart and makes 1 H positive, it's going to make 1 OH negative, isn't it? If 1 couple gets a divorce, you're going to have a single guy and a single woman, aren't you? Okay? So now we have the exact same value for the hydroxide concentration. they have to be the same because when a water molecule breaks apart, it makes one of each. And that's how we're able to determine that the pOH of water is also 7. Okay? So what's our value for Kw? 1 times 10 to the negative 7th times 1 times 10 to the negative 7th divided by 1 is 1 times 10 to the negative 14th. 7 plus 7 is 14. You can see where the number 14 comes from. Why do we have the number 14? Why is it our scale goes from 0 to 14? It's because that's the way water naturally occurs. Okay? One more little thing about your acids and bases before we talk about our experiment is that I started today's discussion, and we'll work mostly in this unit with what we call monoprotic acids. Monoprotic, one proton being given off. But sometimes we have some diprotic acids. Diprotic acids, such as sulfuric acid in our strong acid discussion last year, means that it gives off 2 protons. Okay? And so that throws a little bit of a twist into some of our calculations with sulfuric acid, but also with some of our weaker acids that are, or weak acids which are diprotic. I'm going to start off with a molecule that I'm going to call a generic diprotic acid, and that generic diprotic acid is H2B, okay? H2B. And this doesn't stand for boron. I guess I could use another variable. But anyway, what happens with this fella is, and we got to think about the collision theory, and we got to think about what's really going on with our particles when things actually happen. I'm going to take this molecule, I'm going to dissolve it in water. And the first thing that happens is that one of the hydrogen ions, one of the protons, will leave the molecule, okay? We don't believe that it would just have both of them leaving all at one time. We would have one of them leaving first, okay? And forming this intermediate particle in the dissolving process, Hb with a -1 charge. Why does it have to be negative? Well, because if you lose an H positive and you start it off neutral, then this will be negative, okay? That fellow will then eventually break apart. Now, that it may take more time depending upon what it is. Some of the diprotics will lose their first proton real easily, and then, wow, it takes forever to lose their second proton. Some of them will lose the first one and then the second one right away, or at different times. But the bottom line is that it will eventually lose a second proton and become the anion that has a -2 charge, like sulfate has a -2 charge. Okay? So all in all, what's happening here is that this fella is breaking apart, giving us 2 protons and 1 anion that has a -2 charge. Okay? But in studying this, we will see that there are actually 2 K values, all right? And the calculations using the 2 K values I've saved for the enrichment activity as opposed to the required materials, but we will talk a little bit in our required materials about the idea that there are some diprotic acids, okay? All right, well, let's switch gears then and talk about the experiment that we want to do with this unit. And we want to study some acid or base. We're going to use an acid, but we could use an acid or base. And we're going to study a nice weak acid system that is very, very important. And that is, it's called a buffer system. And if you've had biology, you know, or at least studied, that our body, our human body has its own buffering system. And the point of that is that we need to maintain a constant pH. And that's what buffers do, okay? So this is, and again I'm going to start off with the definition, a buffer is a combination of a couple of different solutions that's going to maintain a constant pH. That's the whole purpose of the buffer. Maintain a constant pH. Okay? But we need to define it a little bit more because that's just sort of the application of it. We need to have a constant pH. Okay, so we make a buffer. How do we actually have that? How does that actually work? Well, a buffer is a combination of a weak acid and its salt. Or it could be a weak base and its salt. We're going to use an acid in our lab. Okay, so this is a combination of a weak acid and its salt. Okay? And I'll put a little note down here. Or base. We could use a base too. So what do I mean by a weak acid? Well, we could choose any acid except for hydrochloric acid, nitric acid, sulfuric acid, the strong ones. Okay, so we could choose any of those, and then we could pick out a salt of that particular acid. So in our experiment, what we're going to do is our weak acid is going to be acetic acid. Okay? Acetic acid, and again, it's the same one we've already used today, is the weak acid that is in vinegar. Okay? Vinegar, not only is acetic acid a weak acid, but it's only 5% acetic acid. So it's really, it's not very strong at all. All right? And what would be a salt of that? Well, that would be something like sodium acetate. Okay? We could use potassium acetate or magnesium acetate, but we're using sodium acetate as the salt. So it lends us to go back to think about, well, how do we know that's a salt and what's a salt and where do we get that? Because most of the time when we think of salt, we think of the words NaCl. We think of the formula NaCl, not the words. But we think of salt, we think of just one thing. And we know there are lots of other salts. We studied them in acids and bases. Like, for instance, we might have magnesium sulfate, which is Epsom salts, or we have Rochelle salts, or we have all kinds of different salts that we use in our society and in our laboratories. So what is it that makes something a salt? Well, if we take, for instance, our basic neutralization reaction that we studied in Chemistry 1, we said that an acid plus a base makes a salt plus water. Okay? For instance, we could use one of my favorite equations. All right? I love this guy. Hydrochloric acid, sodium hydroxide makes sodium chloride and water. Well, in this case, sodium chloride is our salt. That's table salt. Okay? In our case, how would we make sodium acetate? Well, we would use acetic acid and sodium hydroxide. Okay? And you see, this is how we end up with sodium acetate and water. Okay? So I hope that makes sense, that this is the salt from the weak acid. Okay? The salt from the weak acid. So we combine these two together to make this buffer, this buffered solution. So what you're going to do in the experiment, you're going to take some acetic acid, you're going to record the pH of it, and then you're going to add some strong acid to it. Okay? We're going to add some hydrochloric to it. And you're going to see that the pH is going to change. Then you're going to take some sodium acetate, and you're going to add some strong acid to it. And you're going to see the pH is going to change. Then you're going to take and you're going to combine the two together. You're going to make a buffer. And we're going to observe that when we add the acid, or we could add base, we could do either way, we're going to hopefully see that pH remains constant. Our human body does the same thing. Even if we get too acidic or too basic of solutions, things coming into our bodies, we need to maintain that constant pH to remain healthy, and that's the importance of a buffer.